Bienvenidos, muy buenos días a todos. Agradecemos mucho el interés que tienen en este webinar, el tercero de la semana, que estamos desarrollando a través de CITEC y nuestras marcas representadas. En esta ocasión, en conjunto con Vibración Research, presentaremos el tema cómo generar un perfil random de vibración. Esta presentación estará a cargo de nuestro ingeniero de aplicaciones, Ryan Becker, quien, seguramente muchos de ustedes ya lo han conocido y han tenido la oportunidad de estar en una reunión con él y con el equipo de CITEC. Él ha estado asistiendo. La presentación va a ser mayoritariamente en inglés. Si tienen alguna pregunta, por favor, no duden en hacérnosla saber a través del chat, en español o en inglés, de cualquiera de las dos formas, no habría ningún problema. Ryan, muchas gracias por acompañarnos nuevamente en este webinar. Pues comenzamos.
Yes, hello, good morning, everyone. As Leonardo said, my name is Ryan Becker. I'm an international application engineer for vibration research. My main role is to cover support customers in Latin America and Asia Pacific. So I'm frequently in Mexico. Unfortunately, during the pandemic, I have not been able to visit for over a year, but hoping to get back very soon. So Leonardo, mark the calendar. We'll make sure to get down there soon.
Sure.
I have over 13 years of experience in test and measurement. So I've been doing this for some time. So again, if you have any questions on these topics or test and measurement in general, please don't hesitate to ask them in the chat, or there's also the question and answer section of Zoom webinar. So make sure that you're interacting. Let us know if there's anything that was not clear. But let's jump into the topics today. So the topic here in English is generating random tests. And so what this is less about entering random profiles and much more about creating random test specifications. So for example, if a customer is providing you with field data and says, you know what, I need a random test that I can run in my lab that will simulate that environment. That's exactly what this webinar is about today. So hopefully, if you're not doing that in your lab, it's really going to help you understand the random test specifications that you are running. Where did they come from, and how did the engineers create them? So let's jump in. The first thing that I like to look at is how can we utilize field data in our lab? Well, there are a lot of ways that we can do it. If we're looking at the vibration research software, here are 6 modules that we have that are targeted at taking field data and playing it on your shaker. The first one is probably the most simple one. It's our field data replication software, the FDR software. That runs in our FDR software module. And what this does is it plays back that field data one-to-one on your shaker. So it takes that time history file and plays it back exactly one-to-one, just like if you were playing a song on a speaker. It's playing it back exactly how it found it, right? And so this can be great because we're always running exactly the same test, the exact same frequencies, the exact same accelerations at the exact same time, right? So it's a very repeatable test, extremely repeatable. Now, let's say we don't want to run this one-to-one test. Let's say we want that test to change a little bit because, as we know, if we drive down a road 10 times, the vibrations that we see won't be exactly the same, right? They'll be slightly different each time. The frequency that we see, the amplitudes that we see, it will change. And so that's why we use random, right? And in our software, we have two options. We can use random import, and that's going to take a time history file and then turn it into a random test. So one time history file into one random test. Now our fatigue damage spectrum option, FDS, what this allows you to do is take time history files from multiple environments and turn that into a test. And then even take that a step further and accelerate that test. So now we're starting to talk about test acceleration, where 1 hour in my lab is equal to 10 hours in the field or 100 hours in the field, right? And a lot of the test specifications are written with some type of test acceleration. Fatigue damage spectrum allows you to do that. Now the sign tracking analysis and generation, the STAG option, this lets you create a sign-on random test. So what we've seen in working with several partners around the world is that sometimes people see failures in the field that they're not seeing in their lab. And whenever we see that, we need to evaluate the test that we're running in our lab. Is it really replicating that field data? Well, what triggered this is a customer was having that issue, and they sent us all the data from the field and from the lab. And we looked at the field data and said, you know what? There's a very large rotational, so a sinusoidal component in the vibration that's being seen. So an example would be a part that's mounted on an engine or a part that's mounted on a helicopter, right? Where there's something rotating that's making a very strong repetitive vibration. So this software allows you to actually take your time domain data and pull out those sine tones and create a sign-on random test. For that customer that we assisted with this, they were able to, after they created their sign-on random tests, they were able to recreate the exact same failure they saw in the field when they switched from a random test to a sign-on random test. Finally, shock. You can run the shock response spectrum or user-defined transient. The way to look at these are, if you want to define a shock pulse in the frequency domain, the SRS option will do that. Or if you want to define in the time domain, the UDT option. So this is often used for earthquakes. People will take a time history file of an earthquake or a simulated earthquake and play it back on their shaker. So the three things that we'll be focusing on today are going to be random import, fatigue damage, and the STAG software. These three options are all random tests, right? So let's look at this a little bit deeper. So what is a random test and why do we use random? Well, instead of shock or instead of sine, instead of FDR. Well, as I mentioned, a random vibration is random. It's simultaneously sending out vibrations at multiple frequencies, right? That over time includes a full test frequency range, right? So at any one moment, we cannot predict what frequency or what amplitude will come next at any given moment. Now, the output follows a probability, but we can never say we know for certain what's coming next, right? So we say that because it's exciting all these frequencies at once, because it's very random, we say it's a realistic representation of the real world. So we say that random testing simulates the real world. Random testing also gives us the ability to simulate multiple environments at once. So we can pull in, as we talked about, time history files from different environments, put them together, and then create a test that will simulate all of those environments at once. So if we know that this product can pass that test, it can survive all 3 or 10 of those environments. Finally, we can easily accelerate the test as well. Very easy accelerate the test. And this allows us to save time on our shaker. As you know, shakers are expensive. Shaker time is expensive. And so saving time in our lab can cut down a lot of cost, engineering time. So accelerating a test is a huge benefit. So if we look at the definition of a random test, what do we see? Well, it's defined in how long you have to run it. So how much time, of course. But then it's defined by what we call breakpoints. And the breakpoints define a PSD, a power spectral density, that we're going to replicate on the shaker. In this example, this is a simple NavMat test that has a frequency range from 20 hertz up to 2000 hertz. And so we see these 1, 2, 3, 4, 1, 2, 3, 4 breakpoints. We see that most energy is being applied here between 80 and 350 hertz. Outside of 20 and 2000 hertz, the shaker and controller are going to attempt to limit that vibration as much as possible and essentially focus on exciting this range of frequencies with that random output. So if this is defining the PSD that we want the controller to attempt to replicate on the shaker, well, we need to understand what is a PSD. So PSD, as I mentioned, is a power spectral density. So power defines the magnitude of the PSD. So we can think about how much power is there at each frequency. Spectral, it's defined by in the frequency domain, right? So we've defined a power based upon the frequency. And finally, density, we normalize the magnitude to a single hertz bandwidth. And I'll explain that as we talk about how to calculate it. So if we were going to run a very simple random test from field data, one way we could do it is just doing a PSD of that data. The way to calculate it is we first start with the time domain data. So for example, here's 5 seconds of data from some random vibration. Next, we define that, or we divide that into different frames or sections, right? So as that data comes in, we divide it into sections, which we call frames, and then we apply a window function. So perhaps you've heard of an FFT window. So this is an FFT windowing function. There's Hanning, Hamming, Blackman. So when you're doing an FFT analysis of something, when you're applying that window function, this is what it's doing. It's applying a different type of filter to each frame, okay? And so this is an example of the Hanning type. For your reference, this is also an example of a 0% overlap FFT. If you've seen that setting in your controller or FFT analyzer, where you can set 50% or 75% overlap, you start to see the frames will overlap each other. So there'll be frame 1 and frame 2, and that's so you don't lose all of this data. So overlapping is a little beneficial because you don't lose and filter out so much of the data as when you're doing a 0% overlap. But once we apply that window, each frame is turned into an FFT. Once we have the FFT, you'll see we have acceleration over frequency. So before in the time domain, we really couldn't see what frequencies were in that data. Very, very difficult looking at it. But now, as an FFT, we can see, okay, wow, there is a lot of power between roughly 20 hertz and 2000 hertz, right? So we start to see what frequencies are present. Next, we do that to all of the frames. We square them to get the power spectrum, and we average them. And if you've heard of the term degree of freedom, so when you're defining a random test, sometimes you need to enter this value called degree of freedom, DOF. Well, DOF defines how much averaging there is, how much time we're looking at, right? So if you have a very low DOF, you'll see that the random signal has a lot of variation, right? It's very jagged. But if you have a high degree of freedom, you have a lot of averaging, so you have very little variation at the end. So finally, we take that power spectrum and we divide by the analysis bandwidth to get it normalized to 1 hertz. So that's how you get the G squared per hertz that we use to define the PSD. Once we have that PSD, now we can take that, put it in our random profile, and run that random test. And that would simulate essentially an environment very similar to the vibration that we saw in the field in our time history data. Okay. Now, let's say we want to do some test acceleration, or we want to simulate multiple environments. Well, if we're just calculating one PSD, we can't do that, right? So I want to first show you an example of test acceleration and multiple environments being simulated in an actual test. So here's an example of the MIL standard 810H test. I just happened to pick this one. I looked up the specification and I looked at inside the 514.8, which is the vibration section of the test, Annex C. Then I found the category 4, which is for a truck and trailer. And this is for secured cargo on a common carrier. So that means a pretty standard truck where the cargo is secured inside of the truck and the truck is going over US highways. So that's what this test does. It says that, look, if you can run this test successfully, you should be able to survive this portion of shipment, right? And then MIL standard 810H also has other standards that define all these other modes of transportation before it gets to its end use. Of course, MIL standard 810H is a military standard, so it focuses on military transportation. But again, here, you can see what they've done is they've taken data from trucks that were driving all over the US in California, Florida, Chicago, New York, because there's different types of materials used in the road. There's different types of quality of road. And they took all that data together and they processed it into a random test and said, look, if you can pass this, you can survive those environments, right? The average of those environments. Now, instead of forcing you to simulate 1 hour on the road and 1 hour in the lab, they also accelerated the test. So if you read this, what it says is 1 hour of testing is equal to 100 miles. Well, if you know, normally 100 miles takes us over 16 hours to drive, right? So there's some type of test acceleration being done. If we look at this profile, we see that they've created a profile for the vertical, transverse, and longitudinal axes. And so let's just look at the vertical axis, for example. Here are 3 of those breakpoints. We can see that there's a high amount of energy here at the lower frequencies. So it looks like up between 5 and 40 hertz. And then it significantly starts to drop off in the vertical axes, right? What this test is saying is that if you can survive running the test for 1 hour in vertical, 1 hour in transverse, 1 hour in longitudinal, you'd be able to survive 1,000 hours on the highway, right? So what I'd like to answer with the next portion of this webinar is, how did they do that? What types of software tools did they use to come up with these values to create this test? Well, we'll look at that here. An example of that would be the fatigue damage spectrum software. Fatigue damage spectrum is a readily available thing to use. It is a market standard. So you can go up and look up the calculations and do them yourself in MATLAB. but the vibration research software does make it easy to pull in everything and calculate it. So when we talk about fatigue damage, what do we mean? Well, we're talking about the damage that's being applied over a large amount of cycles. So we're not talking about a big shock test where the product is damaged in one shock, right? We're talking about calculating damage that's applied over many cycles of vibration. Right? So an example here would be this cantilever beam, and essentially running a test and determining how much damage needs to be applied to break this beam, right? We can use fatigue damage to calculate that and create a random test that breaks that beam within a certain amount of time, right? How is that FDS calculated? How do we calculate the fatigue damage? Well, what we do is we take the time domain data and then we process it and filter it. So by filtering it, we're just looking at a certain small range, frequency range, to understand what's happening at that frequency. So here's an example. We apply a filter to look at only 20 hertz data. And we see here all of these cycles. And what we do is we then apply a rain flow cycle. And what that does is really just count these peaks. At 20 hertz, how many peaks are at what amplitude? So you see here's the amplitude. As the amplitude gets higher, there's less and less. We add up all of those to determine how much damage is applied over that certain amount of time. And then finally, we take all of those frequencies and we create a fatigue damage spectrum. So over every frequency, how much damage is being applied. Once we understand that, once we understand how much damage is being applied at each frequency over a certain amount of time, we can now use what is called the Henderson Pearsall method to convert that FDS to a PSD, which we can run in our lab. So that allows us to take all of those time history files from multiple environments, calculate how much damage is inside of those, and then create a random test that simulates that amount of damage, or that accelerates the test and applies a certain amount of damage in less time. Okay? All right, so hopefully, if you're totally confused, hopefully the next section will become a little more clear, because I'm going to take you into the software and show you how an engineer would do this live. So let's see here. I need to open Vibration View is open, but ObserView is not. So the ObserView software here, this is a free to download time history analysis software. So what you can do is take your time history files captured from any data acquisition system and copy, paste it, put multiple files together, taper the data so that it's ready to be played on a shaker, right? You can also do FFT analysis in the free version. So there's a lot of capability here. But what we're going to be simulating today is a bike ride. So let's say we're designing a random test that we can do in our lab that's going to simulate being on a bike, a mountain bike specifically. So here I have this time domain data. I'll show you, here's the GPS data from, so just if you want to know, it was taken here in Grand Rapids, Michigan. And that's where Vibration Research is headquartered, here in Grand Rapids. And then I can show you the video here as well. Oh, I need to zoom in a little bit. So you can see that we had several GoPros mounted on these vehicles. And then we also had accelerometers mounted all around the bicycle. And so what we're going to be talking about today is simulating if we wanted to develop a product that we're mounting on this bicycle, how could we go about doing that? How do we create a random test that we could do in our lab? So I'll just play this so you can see an example of this bike ride here. The main accelerometer that we'll be focusing on is the one here mounted on the front fork of the bike. And so what we can do is take that time history, and I'll close this here so it's easier to see. And we can just simply process a PSD. Okay. And so now I've processed a PSD. Of course, I can adjust the parameters and so on. But if I just wanted to run a simple random vibration test, I can go ahead and just copy this, take this over into my controller software, and let's start a new random test. And go ahead and just paste those breakpoints in there. So what this would do is allow me very easily to run that random test. So I'm removing some of the lower and higher frequencies so I can run it on my shaker. So let's say, here's a good one, call that last. So now it's running between 5 Hertz and roughly 2000 Hertz. And I could run this test. Let's look at the schedule. The schedule says 1 hour. So 1 hour on the shaker will be the equivalent of mountain biking in that section for 1 hour. It's a random test that's simulating being on that mountain bike, right? We can also do this with what's called random import. If you remember, we talked about how you can do random import. This would be just pulling up the file, and then it would automatically process it and then create the PSD. There are a couple different settings that you can use to find how many lines, how many points you want to have in it, or if you want to do peak hold versus average. So peak hold would be a worst case. Average would be more of an average of, the average bike ride, I guess, if you will. The peak hold would hold the max amount at each frequency. And then we could run that test. But let's say we would like to combine multiple environments, as we said before, or we want to apply test acceleration. Well, what we would use in that case is the fatigue damage, FDS. And that's that FDS software I was talking about. And the way to do that is click on Add Items, and you can add as much data as you'd like. So here I got this mountain bike data, and there are several channels in here, but let's just imagine that these are multiple environments or multiple files. So perhaps we're simulating here, biking in the city. Here is biking on a mountain, and here is biking on the beach. So that we're simulating the actual end use of the bicycle in multiple environments. We can then just go ahead and click Scan, and then it's processing. It's taking those time history files and calculating the FDS, the fatigue damage for all of those files. It's almost done here. It's calculating all of them. And now what you'll see those 3 files that we have. And then also this blue line is what we call the envelope. So that takes the maximum fatigue damage at all points and then draws a line around them. And then it's going to use that to create a random test. So if we wanted to just create a random test, just like this, we go ahead and select Create Table. We see here that the total target life of this is only 3 minutes, so not very long. So the test duration of 3 minutes would be the equivalent of running these tests or biking in these environments, this one for 1 minute, this one for 1 minute, and this one for 1 minute. So I created that table, and now I have that here, and I can go ahead and just run this. And that would simulate a random test that would be able to survive all 3 of those environments, right? Now, let's say we don't want to run a test that is simulating one-to-one in terms of time. So for example, if I want to simulate 1 hour of biking, I would have to run a 1 hour test. But in our case, we'd like to adjust it a little bit. So what we can do is, let's say this is our mountain. We say that a mountain bike in its lifetime, or we're designing the product to survive the equivalent of, let's say, 500 hours of use in the mountain. Oops, I should say 500 hours. And then in the city, mountain bikes only spend 100 hours. And finally, on the beach, maybe they only spend equivalent of 20 hours. And so as an engineer, I'd have to decide, okay, where do I spend most of my time? In what environments do I want to favor? So this says, okay, I'm making a test now that's the equivalent of a target life of 620 hours. And of course, because if I'm running that at 1-to-1, it would take 620 hours in my lab. If I want to accelerate that, let's say in a 24-hour test, I could set test duration to 24 hours. And now what it's done is looked at it and said, okay, I want to apply 620 field hours of damage in 24 hours in my lab. So I click on Create Table. And now, if I ran this test, it would simulate 620 hours in those environments in just a 24-hour test. So that's how we do test acceleration. Okay. Lastly, I'd like to show you how we generate a sign-on random test. Actually, the random is done the same way. I'll show you that. Let's go back to ObserView software and let's change to some data that's more appropriate for a test that's has some type of rotational component. So I'll go to File, ObserView Recording, Engine Test, and I'll open that up here. All right, so this just has one channel, but you can see this is data that's from an engine. So there was a customer out there that had a problem with a sensor on an engine. And as I mentioned before, they were seeing field failures, but they weren't seeing failures in their lab. And the reason is because products mounted on an engine, as you can imagine, as the engine moves because of its RPM, it creates a very strong sinusoidal waveform that follows the RPM of the engine. So the way we create a sign-on random test is first we must understand what those frequencies look like. And the way to do that is with a spectrogram. So I create a spectrogram that allows us to look at the RPM over frequency. So let me lower this a little bit so it shows up a little bit clearer. Okay. So now we see these lines, right? Well, what does this mean? Well, what it's showing us is as the RPM increases, we also see the frequency increasing and the acceleration increasing typically, right? So obviously here, I think this is it's the third order. We see the strongest vibration. And as that engine ramps up, we also see the acceleration. Well, the acceleration stays roughly the same here. There is a resonance out here at the higher frequencies. But looking at this, actually, let me go to order analysis. I can apply the order so we can see them. But if we wanted to simulate this type of the engine ramping up, ramping down, ramping up, ramping down, and this type of sinusoidal waveform, what we would need to do is a sign-on random test. So we would take all the random and all of the sine tones and put that together. So with our stag software, what it can do is it goes through that data and looks for all of those sine tones. So all of those orders that we saw, and it tracks the acceleration over the frequency. And then what it lets us do is take those sine tones and export them to vibration view, well, or a controller software to be the sine tones that are running on top of your random. So if we were making a sine on random test, what we need to do is extract the sine tones from the data, take that random spectrum, and then put the sine tones back on top in the vibration view software or in your controller software in general. Okay. So I know I've been talking quite a bit here, but I've gone through most of everything that I'd like to do today. So I'll put this back up. But I'd like to open the floor now for any questions that you may have. I'd be happy to go through the software and show you how to do something, or go back through some slides if you have any questions. But I'll let Leonardo take over now and perhaps just summarize some of the things that we talked about today, and then close us up and open for questions.
Well, thanks a lot, Ryan. It was really amazing, the live demo and the slices. It was really, really amazing. So, no sé si tengan alguna pregunta, algún comentario, alguna aportación, por favor, son bienvenidos. Sabemos que este es un tema que no se puede abarcar en una hora, pero de todo lo que pudimos ver, si hay alguna duda, por mínima que sea, tenemos tiempo para verificarla. Ryan, hay una pregunta que dice, si yo tengo otro sistema de adquisición de datos de otra marca, ¿puedo trasladar esa información en el dominio del tiempo hacia mi sistema de Vibration View?
Yes. So there are several ways to do that. Let's look at that. So inside of Vibration View, if you have the time history file, what you can do is, if you go into random import, where is the file type? The file conversion type. Sorry, I need to open it here. Sorry, it's moved in the latest version. When you come inside, you can see that there are several different file formats that we accept natively in both the Vibration View software and the ObserView software. So if your software can support TXT or CSV, different ASCII files, DAT, the ObserView software, let's see, I think it accepts, oops, let's open that file. So CSV, TXT, RPC, UFF, VFW, WAVE. So if you'd like to do this process and you have data collected from any data acquisition system out there, you can also do everything you saw today.
Okay, thank you. Here is another questions.
Mm-hmm.
Can I make this analysis if I have another software? And I send data loggers inside the trailers to have shipping information, but all the information that I have with that USB is in Gs.
Mm-hmm.
Can I use this information and analyze with this system?
Yes. So, Veronica, thank you for the question. Yes, you can do this analysis with other software, but the software will have to have this capability. So I don't know which software you have, but potentially, potentially. I'm not sure about the sign-on random test generation. I know that software has a lot of different things that are targeted more at strain-based fatigue as opposed to vibration-based, but you would have to check with them. But the concepts are open and available. So yes, if you have that data, I'm sure with that software, you can calculate a PSD. So you could calculate the PSD and then just run that PSD in your controller software. And then the second part of the question was about the data loggers. All the data is in Gs. Can you use this information? Yes. All the data is in Gs. That's what we're using now. Right? So all this data you see here is also in Gs. So we can use both acceleration and velocity for the majority of this. All right. There was another question.
Yes. Dice, ¿existen bases de datos con información sobre vibraciones en diferentes ambientes?
That I'm not sure about. If there's a database, I think the best resource would be the test specifications. I don't think there's one standard out there that says, okay, this vibration is this way. But the standards such as ISTA, NAVMAT, MIL standard, these organizations attempt to define a standard for each vibration environment. So if you were developing a test for your product, you'd probably want to use some insight from what others have done before in those testing standards.
Mr. Guerrero says, the complement, por ejemplo, datos recolectados en campo por alguien más y que estén disponibles en bases de datos.
Let's see. Oh, I understand now. So Francisco, I'm not aware that anyone collects this data and makes that data available publicly. But again, the testing standards, at some point, they collected data and then created the random test to simulate that data. But I don't know of any public database where this vibration, time history vibration data is available.
Okay.
Ooh, we got a question from our buddy, Mr. Perez.
Perfect. Yeah, Mr. Erwin Perez, gracias por atender el webinar.
Yeah.
It says, how many data do we need as a minimum from the real environment to have a reliable accelerated test?
It's a fantastic question. To be honest, it's not something that's defined. It's really not something that's defined. What we generally say is you don't want to accelerate too much past 10, but 10 times. But you would need to determine yourself how much data is really required to get an average of those environments. So I'd say unfortunately, it's something that you need to define yourself, right? Because what does an average look like to you? If you took data from one truck that went across the country, that wouldn't be a good data set, right? You'd want to send it on multiple trucks all over the country, aggregate that data back. And of course, that's going to be much more representative of the country as a whole, right? So unfortunately, there's no clear answer, but in terms of test acceleration, we generally say you don't want to go much more than 10 times. So that MIL standard test was roughly about 10 times acceleration, but it depends on the product. It really depends on at what point do you start damaging the product almost as a shock test instead of multiple cycles, right? Where do you cause plastic deformation, fatigue in the product as opposed to damage from repeated vibration? I hope that answers your question, but Mr. Perez, if you have some time, you can always call me, and we can discuss. If you have a live application, don't hesitate to reach out.
Ok. ¿Hay alguna pregunta adicional? Muy bien, al parecer ya no hay preguntas adicionales, Ryan. De cualquier manera, si hay alguna pregunta, alguna duda, alguna requisición nueva para sus pruebas en su laboratorio, por favor no duden en contactarnos. Estamos aquí atendiendo todo el tiempo sus nuevos requerimientos. Nos gusta conocerlos y, bueno, de CITEC, de su servidor, Leonardo Bonilla, o directamente con Ryan. Los dos estamos para atenderles. Muchas gracias nuevamente por atender este webinar. Si existiese algún tema en particular que quisieran ver, del que quisieran aprender más, podemos desarrollarlo para ustedes. Esa es la finalidad de estos webinars, dar a conocer información nueva que les con el desarrollo de sus pruebas en una mejor manera. Les estaremos informando oportunamente. Muchas gracias nuevamente, y muchas gracias por atender esta sesión.
Yes. So thank you, everyone. It was nice to have the opportunity to share a little bit about how to generate random profiles. As Leonardo said, don't hesitate to contact us. Thank you.